artificial intelligence and fundamental interactions. He's won early career awards from the Department of Energy, as well as a presidential one from the White House. And he's been named a Kavli Fellow, a Sloan Fellow, and a Simons Fellow, among many other honors. I should say that ever since Jesse's days as a graduate student, and certainly throughout his work today, he's really known for groundbreaking work that opens up new horizons for fundamental physics. He's well known for his work on collider physics, machine learning, and quantum chromodynamics, especially his work in the context of jets and jet substructure, and theoretical frameworks beyond the standard model of particle physics, in particular dark matter and supersymmetry. And his fresh take on any physics topic that he sort of puts to his mind, I find to be really remarkably inspiring. And certainly personally, he's been an influence on my own attitude in physics research as well. And in this spirit, he's going to tell us today about how particle physics meets machine learning. And let's give Jesse a warm Israeli welcome. I'm going to unmute everybody so that we can hopefully all really be able to hear each other. Let's see. Wait, can I unmute everybody? I wanted to do a nice clapping. Thought it would be nice to attempt to hear. Does anybody know how to unmute everyone? Hold on. Is there a way to unmute everyone?
On participants. Press participants and then unmute all.
Sorry guys. Participants. Okay. Well, I'm not managing to unmute everybody right now, but welcome Jesse. Anyway.
Okay, well, thanks so much, Uni. And so I just hit the mute all button. So all you're going to be hearing is for me from now on. So I really wish I could be there in person. I've only visited Israel once, but I had a wonderful time, and really looking forward to returning again. And in fact, there's money that will help me at MIT actually collaborate with folks in Israel, and hoping to use that money soon whenever they let us get on a plane again. So I'm going to be talking about research at the intersection of particle physics and machine learning. And let me just make sure my cursor is there. Great. And the title of my class, title of my colloquium, normally I'm actually teaching at this hour in the morning. So the title of my colloquium is Collision Course. And as you'll see, I mean collision course in two senses of that word. So before I get there, let me tell you about another collision that's going on. So I am the new director of this AI Institute. It has an unpronounceable acronym, but we pronounce it IPI. And the goal of this institute is to advance physics knowledge from the smalling building blocks of nature to the largest structures in the universe, and galvanize research innovation in artificial intelligence. And this fusion of two fields is represented by our logo here. You can either read that as a capital A with a lowercase I on top of it, or an F and an I standing for fundamental interactions. And we really see these as two sides of the same coin. And you're going to see elements of this in my colloquium today. So I mentioned that I have two different meanings of collision course. So one meaning of collision course is to teach you a little bit about colliders. So I'll give you a crash course in particle physics and remind you that when you slam together protons at high energies, you can probe the fundamental nature of matter. And one of the things that, as Unit mentioned, I work on is this topic of jets. And so you're going to see a lot of pictures of jets in this talk today. But there's another meaning of collision course, and that's a collision of two fields. And this kind of became obvious to me in January of last year, when there was a workshop at the Aspen Center for Physics talking about this intersection of the fields of theoretical high energy physics and mathematics, statistics, and computer science. And the merging of these fields, or the collision of these fields, is generating some interesting outcomes. And so what I've learned to appreciate is that we can gain new insights into particle physics facilitated by advances in machine learning. And maybe these asterisks here are just to emphasize that it's not just particle physics. Many areas of the physical and natural sciences have benefited from machine learning techniques. And when I say the words machine learning, actually that's part of a broader umbrella of these mathematics, statistics, and computer science tools that are now starting to become a bigger part of our research program. And one of the goals of this institute is not only to gain insights in particle physics from machine learning, but do it vice versa. And that's something that we're excited to develop over the next 5 years or so. So in this colloquium, I'm going to be telling you about two anecdotes. And so I'm going to try to explain to you these pictures here. So on the left-hand side is the first anecdote, which is going to be teaching a machine to think like a physicist. This is work with my students, Patrick Kamitsky and Eric Metodiev. So Eric just graduated this year. Patrick's going to be graduating next year. They're fantastic, and they've actually been leading a lot of the efforts that I'm going to be talking about today. And then on the right-hand side, letting collider data speak for itself. So in artificial intelligence language, you would say that this is unsupervised machine learning. And I'll try to explain what this picture is. And this is work with Patrick, Eric, as well as two MIT students, Radha Masandria and Preksha Nayak. And in both of these anecdotes, we're going to be talking about data analysis strategies motivated by the symmetries and structures of particle physics. Now, I'm a theoretical physicist, so it's not just about pretty pictures. And part of the reason why I'm excited about this talk I'm giving you today is that behind these pictures, there's actually fundamental concepts in quantum field theory that these pictures actually represent. And on the left-hand side, we'll see that that kind of psychedelic image is about exploiting a core prediction of quantum chromodynamics, or QCD. And on the right-hand side, you'll see that there's some interesting connection between that picture I showed before and the nested singularities of gauge theories. And I'll explain what those things are in this talk. And we're gaining new perspectives on key theoretical concepts by using this lens of artificial intelligence. So here's the outline for the rest of my talk. So as I promised, I'm going to give you a collision course or a crash course in particle physics. So very quickly tell you about the basics of particle physics. And then my two anecdotes are related to these two questions, which are quite simple at the face of them. So what is a collider event? And we'll think about the data structures of what collider events look like, and that will lead us to a certain type of supervised machine learning technique. And then the question about when collider events are similar, that will lead us into optimization problems and optimal transport. And that will turn out to be related in kind of an interesting way to the structure of field theory. Okay, let's start by a bit of a particle physics 101. So this is a representation of the standard model of particle physics in kind of pie chart form, where you're seeing the orange quarks, the green leptons, the blue force carriers, and the purple Higgs boson at the center of it. And for the perspective of collider physics, actually, very few of these particles do you ever see directly. The only of these particles that actually hit your detector are those that suffer from only electromagnetic interactions, so photons, electrons, and muons. And every other particle in this chart has to be inferred. And in particular, if you take quarks and gluons, they confine under the QCD strong force. And so we don't see quarks and gluons directly on the detector. Rather, they get bound up into bound states in the strong force. And the ones that hit your detector are just the most long-lived ones: pions, kaons, protons, and neutrons. And everything else in this chart has to be inferred from these relatively small number of final states that actually hit your detector. So it's a fascinating inference problem. How do we go from seeing the collision debris that's only of a small subset of the ingredients of the standard model and actually infer the structure of the standard model itself, as well as try to look for evidence for physics beyond it? And so this is a data science challenge. Just to emphasize, this challenge is not just about these particles hitting your detector. The detectors themselves have multiple pieces to them: tracking, hadronic calorimetry, electromagnetic calorimetry, as well as muon systems. And somehow you have to synthesize all that information at an extremely fast rate. Every 25 nanoseconds, there's a collision at the Large Hadron Collider, and somehow infer from these beautiful pictures of these collision events what's going on, even whether to write that information to tape. And I like this representation of a collider event. I think it's quite beautiful. It also represents my field. You see these orange cones. These correspond to these collimated sprays of particles called jets. And there's a variety of data science, machine learning things that you'd like to do with this data, this form. And do a better job of the inference about making measurements of what you see in the final state and inferring what the underlying dynamics is. And one strategy for doing this is, of course, machine learning, which is the topic of this colloquium today. And machine learning in its various forms have been around for a very long time. I mean, linear regression can be thought of as a type of machine learning, and that's been around basically forever. But really what's happening is the rise of deep learning architectures that are able to accomplish tasks that previously were thought to be too difficult to address with machine learning techniques. Now, I'm a theoretical physicist, so I like to do pencil and paper, chalk and chalkboard calculations, and I was skeptical that machine learning would be able to give us really that much in terms of additional insights. But my mind started to be changed when I started to see in other areas of machine learning research outside of the physical sciences, things that were so magical that I realized that actually a deep understanding must have been gained in order to accomplish those tasks. So here's an example of a task that started to change my mind about what machines could do. So this is what's called an in-painting task. So here we have on the left-hand side a picture of a library with various pieces of that image masked out. And on the right-hand side is a reconstruction of the machine's best guess about what's hiding behind those masks. And you can see it does a pretty good job. It captures the regularity of the books on the bookshelf. And the standard lore that we say about why machine learning is so effective for tasks like this is that we say we have massive increases in computational power, as well as large data sets. And if you've seen 1 billion images of a library, then you've seen them all. And you can basically just, based on the prior of what all libraries look like, you can do your best guess about what the reconstruction of the masked regions are. But what started to change my mind is to realize that this particular example was not a situation where you had gigantic data sets. In fact, this was a machine learning architecture that had never before seen a picture at all, nevertheless that of a library. And this is the merging of deep learning with what I would call deep thinking. And progress was made in this case by understanding the structure of the problem and realizing that even without seeing any images, you can make guesses about the regularity of the structures that you're seeing, some type of almost kind of quasi-translation invariance. And you can encode that information into the machine learning architecture. And that's going to be something that we're going to be doing in this colloquium today. We're going to be encoding kind of the principles of physics into machine learning architectures and thereby be able to do better jobs on a variety of tasks. So an example of a task that's in some sense the simplest one that I know in my field of jet physics is to tell the difference between a quark jet and a gluon jet. So you have a spray of particles hitting your detector, and that jet could arise from a quark, which carries color charge of 4/3, or a gluon, which carries color charge of 3. 3 is equal to 9/3. 9 is bigger than 4. So kind of at a cartoon level, gluons are 9/4 as big or as multiplicitous or as wide as a quark jet is. And this is a task that you can think of as like the hello world of jet physics, the kind of the simplest thing that you could write down. In machine learning language, this is just a straightforward binary classification task. And what you're looking for is you're looking for a classifier H that takes in the information that you see in your detector about that jet and tries to output 1 if that jet comes from a quark and 0 if that jet comes from a gluon. A very simple task, one that I'd thought about from a theoretical perspective for quite a while, but in particular in an article in 2017. And what we know is that the best you could ever possibly do on this task is what's known as saturating the Neyman-Pearson lemma, where the classifier takes the following form. It's the ratio of the probability that that jet arose from a quark divided by the probability that that jet arose from a quark plus the probability that it came from a gluon. So if you're in a region of phase space where the probability of having a gluon is 0, that jet arising from a gluon is 0, then you get 1, which is exactly what you would want for the quark-enriched region of phase space. And vice versa, if there's no probability of that jet arising from a quark, then this thing would give you 0. But more generally, you have a fundamental ambiguity about whether something's a quark or gluon, and the best you can do in terms of the best guess that you can make is take this particular combination of the probabilities. And essentially one way of thinking about what machine learning is doing in this context is that if you see a bunch of quarks and a bunch of gluon examples, either taken from synthetic data or real data, you can try to, as best as you can, estimate this optimal classifier. And as we'll see, machine learning can do a very good job on this task as well as other ones. And maybe just to say why this particular simple example might be relevant for the field of particle physics, here's an example of the use of a binary classifier like this in the search for new physics beyond the standard model. So in this case, the classifier is a very simple machine learning architecture called the boosted decision tree. The inputs are various properties of that jet, its jet mass, its width, the number of charged particles inside of it. Signal is quark enriched in this case of gluino pair production decaying down to 4 quark jets and 2 neutralinos. The background is gluon enriched coming from multi-jets, mostly coming from gluon production. And here you see an example of what this optimal classifier would look like, where the background is pushed towards 0, the signal is pushed towards 1. There's irreducible overlap, but nevertheless, you can take advantage of this quark-gluon separation in order to increase the reach in discovering a gluino or a neutralino, pushing it by kind of hundreds of GeV higher by using techniques like this. So this is a study back from 2017. Things have improved dramatically over the past 3 years. I'm not going to show an update of this particular analysis, but just give you a sense of the things that you might be able to do with a quark-gluon classifier. And I can tell you more about that in backup slides if people are interested. Okay, so that was a crash course in particle physics. So hopefully you get a sense that we have complicated data sets. We want to do various types of data analysis tasks with it, and that machine learning is one way of doing those tasks in a better way. So how can we do it in a better way? Well, one way we can do it in a better way is if we account for what we know about the physics of the problem. So let's answer a little bit more detail. What is a collider event? And from a theoretical physicist perspective, all a collider event is, once you've taken into account all of the detection apparatus, is just a collection of points in momentum space. Okay, so we have the collision point at the center here, and out flows these sprays of particles. And each one of those particles represents a 4 vector telling you how much energy and momentum in the x, y, and z directions are coming out of that point. So we have a collection of points in momentum space, basically energy, px, py, pz, for like order hundreds to 1,000 particles in the event. And that's our fundamental data structure. And we need to take data structures like that at every 25 nanoseconds at the LHC, take data structures like that and do our best data processing with that as we can. Now, this type of problem, collections of points in momentum space, actually shows up all the time in other applications of machine learning if you replace momentum space with position space. So if you have collections of points in position space, so this is what's known as a point cloud, and one of the most famous examples of a point cloud are the LiDAR point detectors that you get from self-driving cars. So you have a self-driving car looking at its environment, taking points not in momentum space, but in position space, so the X, Y, Z position, as well as time of the of these LiDAR point detections. And this data structure basically has the same form as the collider physics example that I showed you before. And in fact, some of the tasks that you'd like to do are quite similar. So for example, in these boxes, you see an example of a segmentation task where you're trying to identify points that are associated with each other. On the collider physics side, that corresponds to finding these jets, finding these collimated sprays, and finding what regions correspond to that bundle of particles. I mentioned that one thing you'd like to do with jets is try to tell whether those jets came from the production of a high energy quark or a gluon. Well, quark-gluon classification, the analog of that in the self-driving car case, is you want to tell the difference between a bicycle versus a car versus a pedestrian. And there's other types of tasks that you need to do. You need to do noise removal on the LiDAR side. And then in the particle physics context, there's what's called pile-up, multiple proton-proton collisions when the beams cross, that generates contamination that you need to clean up. So a number of techniques that are potentially applicable in both domains. But one key difference that we have in particle physics is that we actually know a lot about the structure of the problem. So instead of using off-the-shelf point cloud processing techniques, we want to take into account our domain knowledge about how particle physics works and use that information to decide what type of machine learning architecture we'd like to use to solve our problems. So let me tell you a little bit more about the way that jets are formed in quantum chromodynamics. So at short distances, we slam together protons. Protons themselves are basically just bags of quarks and gluons. And the default thing that happens when those quark and gluon constituents collide is you just generate more quark and gluons in the final state. So you generate high energy quarks and gluons. They shower and radiate, generating more quark and gluonic radiation, until you get down to a scale where the strong interaction becomes strong and the quark and gluons bind into making composite hadron states. And those hadron states hit your detector. So this is a quite complicated process, and actually trying to understand every single stage of this process is quite challenging. But one thing that we can do is we can take advantage of our theoretical knowledge about the jet formation process and try to focus our attention on that information which is most robust to this hadronization and detection stages. And so from a theoretical perspective, one of the things that we can do is focus on the flow of energy the flow of energy from the collision point off to the celestial sphere at infinity. And that information is the most robust information that we have to this hadronization and detection steps. So this energy flow operator, it's a quantum mechanical operator. It's built out of the stress energy tensor. So T mu nu, but here we have the zero component, that's energy. The I component is the flow. We take the long time limit. This energy flow operator is essentially the information that I have the most theoretical control over. And it's the one that I want to use in order to build my machine learning architecture. I want to bake in a machine learning architecture that focuses on this most robust and trustable information. So using this, we can try to teach a machine to think like a physicist. So what do I mean by that? So the standard kind of cartoon of machine learning is we have a black box of the machine that you input it some properly specified problem. It might be quark-gluon discrimination, it might be jet segmentation, some other noise removal task, but there's some properly specified problem. And then you hand it many examples of that problem already being solved in some way. So if you know, for example, that you have a pure sample of quark jets and a pure sample of gluon jets, you can feed those labeled examples in and then try to learn that Neyman Pearson optimal classifier. And then Apple pop from the black box some solution to the task at hand. But if we want to think like a physicist, there's kind of two things that we can do. One is we can bake in our understanding of the structure of this problem. And there's two things that we'd like to bake in. One is a symmetry that we know from quantum mechanics, that in quantum mechanics, we know that identical particles are indistinguishable. So that means that the order in which the particles come out of the collision doesn't have any real meaning. And so we should treat the particles coming out as an unordered list. So just a generic set without any ordering to it. And what that means in particular is that we can't use machine learning architectures based on natural language processing, because with natural language processing, the words come in a particular order, and there's semantic meaning to the words being in the order that they're in. Whereas in the particle physics case, all the particles that make up your jet or make up your event, their ordering doesn't matter. And so we want to encode that into our machine learning architecture. The next thing that we want to encode is this notion of energy flow, which in the context of quantum field theory is called infrared and collinear safety. So safety corresponds to one of the things that we want to achieve. We want to have a focus just on this energy flow information. And that means we want to make sure that energy is weighted in the appropriate way. And again, this is something that we could learn from quantum field theory. So one way of thinking like a physicist is to encode the things you already know about your physics problem into your machine learning architecture. Another way of thinking like a physicist is to do what we always do. You know, as a professor, I'll ask my graduate students to kind of verify that their work is correct. And so we want to have some way of interrogating the machine in order to verify that the answer is physically sensible. And so I'm going to show you this now with a machine learning architecture that I built with my students, Patrick Kamitsky and Eric Metodiev. And so the name of this machine learning architecture is called an energy flow network. So it's focusing on this energy flow information. And it's an architecture designed around symmetries and interpretability. So the machine learning part of this equation is just this F and phi functions. Those are parameterized by neural networks. The details of that don't matter. What matters for us is encoding the symmetries of this problem. We have the permutation invariance that's represented here by the sum, when I'm going to sum over all the constituents inside of my jet. That guarantees that the information is permutation invariant. And the fact that I'm weighting my information linearly in energy as opposed to quadratically or some other power, that means that I'm focusing on this energy flow. It's what particle physicists would call infrared and collinear safe. And what's amazing is that this quite simple set of equations. So we have S, the solution, V, the verifying functions. We have L of those verifying functions. And it turns out that there's been proofs in the computer science literature, in particular a proof by a group at Carnegie Mellon, that if the number of these so-called latent dimensions, or these verification functions, if that L goes to infinity, you can provably describe any observable with this permutation invariance and with this linear weighting, any observable that's infrared and collinear safe. It turns out to have excellent jet classification performance, and I can tell you more about that in backup slides if you're interested in. But for me, as a theoretical physicist, I don't really care about the machine solving the problem so much as I want to make sure it solves the problem in a physically sensible way. And this energy flow network architecture was designed with this interpretability in mind, that this latent space of dimension L, I can visualize this latent space of dimension L if L is small enough, or if L is too big, I can try to at least plot this phi function, a per particle function that tells me when a network sees this jet, what information is it paying most attention to? And what you're going to see is you're going to see a head-on picture. The jet is going to come at you. And what you're going to be seeing is you're going to be seeing where the neural network has decided to pay attention to. And we're going to see whether it's paying attention to information in the same way that a theoretical physicist would. Okay, so this gives rise to these psychedelic images that I hinted at the introduction of my talk. So this is training a machine learning algorithm to do quark-gluon classification. And now we want to say, what part of the jet does the machine learning pay attention to? So you should look at each of these rings and imagine these rings are all filled in. So we have filled in rings of basically where the machine is paying attention to. So is it paying attention to this small region at the center here, medium-sized region further out, and then big regions on the outside. And then this latent dimension here is basically how many verification functions am I allowing it to use. So starting with 8, then 16, then 32, 64. And already at latent dimension 64, you can start to see that the machine has learned some interesting symmetry structures. It's learned to pay attention in basically a azimuthally symmetric way around the axis. It's learned that actually these are unpolarized jets, and therefore there's no extra information associated with their orientation azimuthally. And then if I go to the highest latent dimension here, you can see this kind of like fractal self-scaling structure where the machine is paying more and more and more attention to the center of the jet. And it turns out that the machine has basically learned about the singularity structure of QCD. It's learned the way that gluons are radiated off of quarks and gluons. So I can put a little bit more numbers to this by just showing you the way that the machine has learned the collinear structure of QCD. So here I have a quark or a gluon. If it's a quark, it has color charge 4/3. If it's a gluon, it has color charge 3. That tells you the propensity of that quark or gluon to radiate more gluons. This is analogous to the fact that in electrodynamics, electrons will radiate off photons proportional to the charge of the electron. And the angle in which that radiation is emitted, both in the electrodynamics case, but also in the strong force case, it goes like 1/θ. And that 1/θ dependence is shown here in a slightly different form. The distance from the center of the jet versus the pixel size. If the machine had learned the collinear dynamics of QCD, then the slope here would be 2. It's not quite 2, it's 1.6 because of running coupling and non-perturbative effects. But essentially, the machine has learned the way that QCD organizes its information, and that the machine is paying attention in an information theoretic optimal way by paying attention to information that follows the scaling behavior of QCD. So there's a lot more that I could tell you about this example and show you, for example, classification performance and things like that. But the thing that I want you to take from this part of the talk is that we can bake in our physics knowledge about the problem, have the machine do a task, in fact, turns out to do a task better than a human can do. And then we can go back and try to understand what the machine had done. And in this case, the machine had learned something foundational about QCD. And then you can imagine baking that foundational knowledge back into the machine and see what it could learn next. And so this is an example of machine learning innovation driving the field forward in an interesting way. Okay, so that's what I wanted to tell you about what a collider event is. And that's a pretty straightforward application of machine learning. Quark-gluon classification has been attacked by many people with machine learning and non-machine learning lens. I now want to talk about something that even for particle physicists will be unfamiliar, and kind of a new way of quantifying when collider events are similar. And this will turn out to lead us to some interesting unsupervised machine learning strategies for data analysis. So I told you that one collider event is a collection of points in momentum space. So what are two collider events? Well, two collections of points in momentum space. So this is a view in the transverse part of a particle physics detector of a beautiful multi-jet event. One jet is coming from the CMS experiment on the left-hand side, and the other one is coming from the ATLAS experiment on the right-hand side. And ATLAS and CMS are on opposite sides of the LHC ring. And one question you can ask is, well, how close are these collider events? So if I only care about spatial distance, then the distance of these collider events are basically the distance of their cameras. So, 8.5 kilometers across the LHC ring. But that's clearly not a very useful notion of distance. And we'd like to have a notion of distance that captures what your brain sees intuitively. These are both multi-jet configurations. They have a similar number of prongs. They have roughly similar patterns, actually. And if you ignore the fact that ATLAS and CMS have chosen completely different color schemes for representing their collision debris, you would say that these have very similar topologies to them. And we would like to be able to quantify how similar these events are. And given that I just told you all about energy flow, maybe you're not so surprised that the thing that I'm going to use is I'm going to be using the similarity of the energy flows of these two events. And this idea of comparing energy flows, which you can think of as basically distributions of energy on these detector cylinders, the energy flows, comparing those distributions, there's actually a whole field that's devoted to comparing distributions, in fact, with a long history going back to the 1700s, in fact. The way that I learned about it was in the context of computer vision applications. And in computer vision applications, this is called the Earth mover's distance. But this is a problem that has a much longer history. So French mathematician Monge in 1780s was studying the transportation of dirt from one place to another. I guess in French, there's two different words. For a mound of dirt, it's called a déblai, and a trough where you're going to put that dirt is called a remblai. And you want to figure out what is the cheapest way to transfer that dirt from one location to another. This was formalized in the 1960s by Wasserstein, who developed this into what's called now the Wasserstein metric. And then in the computer graphics in the kind of 80s and 90s, this goes under the optimal transport problem called the Earth mover's distance, which is the minimum work, basically the stuff you're trying to move times the distance you want to move it, to make one distribution look like another distribution. And this is the first time I encountered this concept, and we're going to apply it to particle physics. If you've seen this before, I think you'll know that this is a very powerful technique for comparing distributions. For those of you who haven't seen this before, I definitely encourage you to think about how you might incorporate this into your research, because we found it very powerful, and it turns out to give a very intuitive notion of distance between distributions. So what you need is you basically need a notion of dirt, so some kind of additive weight. In our case, that weight is going to be energy. By energy conservation, basically energy adds linearly, so it acts like a weight. And if you have a zero energy particle, that corresponds to a zero weight particle, and zero weight doesn't contribute at all to your measure. The need to have a notion of ground distance. In the collider physics context, we have the geometry of the detector. For the experts, you'd want to look at the distance in the rapidity azimuth plane. That's a useful notion of ground distance. And what this Earth mover's distance does is it tells you how to go from an additive weight and a ground distance and turn that into a distance between distributions. So you can think about having the déblai as being like this blue distribution, the remblai being like the red distribution, and I want to transport the blue to being the red in the optimal way. So in particle physics, we're not moving Earth around, we're moving energy around. So using the same acronym EMD, we introduced the energy mover's distance. This is work with Patrick Kaminsky and Eric Metodiev. And what we defined is an optimal transport between energy flows. So we have an energy flow here shown in red. That's one configuration of a jet sending off radiation hitting your detector. So the square here represents a patch of the detector where a jet has been identified. The blue represents a different jet in a different configuration. And I now want to transport the blue jet to the red jet. And these black lines represent the optimal transportation path to transfer the red energy to the blue energy. This energy mover's distance has units of giga electron volts, so units of energy, and it consists of two terms, a cost to move energy, and for jets that don't have the same amount of energy, the cost to create that energy. And by defining an optimal transport between energy flows, what you get is a notion of distance, and a special type of distance, a distance that's known as a metric. So this is not metric in the general relativity sense. This is not a differentiable metric, but a metric that defines pairwise distances. And it defines pairwise distances on the space of events. So this whole energy flow in red gets summarized to a single point, shown as this red star. This whole energy flow in blue gets summarized to a single point, this blue star. And the distance between these two stars gives you a metric that is positive, and zero only when the configurations are the same. And it satisfies the triangle inequality. And because it satisfies the triangle inequality, you can use this to triangulate the space of events. And that's something that's going to be useful for us in a moment. We talked to a reporter at the MIT News when this first came out, trying to explain what this is. Sorry, let me, we did a test of this before. You should now be able to see the animation more smoothly. 1 second. Okay. So let me just check to see, make sure this is looking good. So I'm just checking my Zoom. Yeah, you can see this more or less okay. So we're talking to a reporter at MIT News and said, oh, it's like building up your social network. Basically, how many neighbors or friends do you have? And indeed, you can kind of think about it like that way. And just like you can ask about the dimensionality of your social network, you can ask questions about like the dimensionality of the space of jets. And what you're seeing here is you're seeing a plaquette of this triangulation where we take 3 different jets, a 1-prong jet, a 2-prong jet, a 3-prong jet. We try to transport one to the other. So the movie in the center of the triangle is showing you the optimal transportation path to deform one to the other. And the amount of stuff times distance that you have to move gives you a total distance between these points. And we see that the 3 energies here, you can check quickly, satisfy the triangle inequality. And if we keep kind of building up these triangles, we can actually map out the space of jets and ask interesting questions about that data set. Okay, so what can you do with a metric? Well, it turns out that you can do a lot, and I have many other examples if you're interested. But let me just show you 3 of them. Okay, so as I hinted before, one thing you can ask is about the dimensionality of your space. So if you count your number of neighbors a distance r away from you, the number of neighbors, its growth, tells you the dimensionality. So if you're living in 2 dimensions, then as most people are living in 2 dimensions in terms of the city blocks that they live on. If you go out a distance r, the number of neighbors grows quadratically. So it scales like r squared. And if you invert this formula, then you can figure out the dimensionality by the logarithmic scaling of the number of neighbors. So if I zoom really close in on this spiral here, I just see a single point, so I have a dimensionality 0. As I zoom out further, I see that things are arranged kind of more or less uniformly in 2D. So now I have dimension 2. And then as I zoom out further, I have a dimensionality of 1 for the arc. And then eventually, as I go out further, I see that the spiral is starting to fill out more of the space. It's dimensionality closer to 2, and then eventually 0 as I zoom out all the way. And so we have a notion of scale-dependent dimensionality, sometimes known as the intrinsic dimensionality. I can do exactly the same thing for collider events, but now my notion of distance is a notion, my notion of scale rather, is a notion of energy. And so now I can study, as I interrogate a jet at different energy scales, what is its dimensionality? And this is something that we did first in a QCD calculation, where the dimensionality depends on whether I have a quark or a gluon. So at very high energy scales, all I see is a single quark or a gluon, so I have a dimensionality of 0. And then as I go to lower and lower energies, so that's longer and longer wavelengths, I see this logarithmic scaling with the dimensionality, such that if I probe this jet at a relatively low scale, I have somewhere between, let's say, 2 and 7 dimensions. So this is a calculation done in quantum chromodynamics. We can check that calculation by actually going to real data. So this is data from the CMS experiment released for public use under the CERN Open Data Project. And Patrick and Eric, together with Radha and Preksha, made this beautiful plot of the correlation dimension, where it's somewhere in between the theoretical predictions for quark and gluon dimensionality, because a generic open data set of jets is going to generically have some mixture of quarks and gluons. And you see, as advertised before, at short distances, we have a dimensionality 0. And then as I go to longer and longer distances, that is smaller and smaller energies, I see this fascinating growth, kind of exactly as you might expect from the process that I told you before about showering and hadronization. So this is one thing you can do with the space of jets, is you can compute its dimensionality. And this is something that I didn't even know how to do without this machine learning strategy. What's another thing that I can do if I have a notion of distance? Well, I can try to take that high dimensional, in fact, fractal dimensional space and try to project it as best I can onto 2D. So that's what's shown in the left-hand plot here. And that's this gray blob. What does this represent? Well, what I did is I took 30,000 jets from this public data set, and I took all 30,000 squared, or 30,000 choose 2, I guess, combinations, and I triangulated the space. Then I take that space, I try to project it as best I can down to 2 dimensions using a technique called T-distributed stochastic neighbor embedding. And that gives me this gray blob. And basically, this is like a histogram, but a histogram in this meta space of jets. That's a very hard thing to visualize. So I've decorated on top of it a bunch of circles that correspond to example jets. And these example configurations weren't chosen randomly. They were actually chosen to be representative of this space. In particular, they're selected using a procedure called k-medoids, or in this case, there's 25 jets, so 25 medoids. These are the 25 most representative jet configurations, meaning that they are as close as possible to tiling the space of 30,000 as I can get. In computer science, you might call this a core set. That is a subset of the full data set that has provably accuracy for any quantity you might try to estimate with it. And what you can see is that this embedding has actually captured a feature of QCD that we've actually already learned about in this talk today, because we learned about the collinear singularity structure of QCD. And what you can see is that one of the dimensions that the machine has picked up on is a dimension corresponding to this opening angle theta that I told you was so important. So if I go off to the left-hand side, I have jets that are basically very narrow and collimated. When I go over to the right-hand side, I see jets that have a wider opening angle. And then there's also this energy sharing fraction Z, which says how much momentum is carried by a radiated particle. And that energy sharing goes roughly from 0 on the bottom part, where you can see very small amount of energy sharing, to more 50-50 split at the top end. And so this is an example of a very cool way of visualizing data from the Large Hadron Collider that, if I didn't know it already, would actually teach me something interesting about the two coordinates, essentially, that are most important for describing the radiation pattern of jets. Okay, so this is one thing you can do. What else can you do? Well, one thing you might try to do is do better than you had done before. So one of the things that I worked on almost a decade ago with Ken Van Tilburg, who's actually now a faculty member, so that's exciting to see one's undergraduate student go up through the academic ranks. And we developed an observable called n sub jettiness, and true to its name, n sub jettiness tries to find basically how well do the radiation pattern of jets align with n prongs of radiation. And the formula for it is kind of a mess. It involves two minima. It involves energies and angles. It's a kind of a complicated optimization problem. And you might say, oh, using this new optimal transport idea, maybe there's some way for me to think about optimally transporting my radiation pattern to my jet axes. And that might give me a better way of quantifying how n sub jetty something is. And what it turns out to be is that if you try to do that optimal transport to the most representative 3-prong in the case of tau3 or 2-prong in the case of tau2 configuration, it turns out that this formula, which seemed kind of arbitrary back in 2011, turns out to be exactly equal to the optimal transport problem, where you're trying to take a point corresponding to this jet and optimally transport it to the closest point along a manifold with of all possible n particle configurations. So far from being a random formula, somehow we had stumbled into the fact that like this is in some sense the natural way of thinking about kind of collider observables to test for pronginess. And in fact, it's not just n sub jettiness. It turns out that there's 6 decades of collider physics that if you just use this geometric language, take this space, triangulate it out, talk about manifolds in that space, points in that space, distances in that space, continuity in that space, it turns out that there's many ideas from the past half century that actually correspond to optimal transport problems. And I'm not going to go through any of these in detail. I'm happy to answer more questions about it if people are interested. And what we're hoping for is that the next half century of collider data analysis will be inspired by some of these same ideas. So this is what I wanted to tell you about this collision course. So kind of even just zooming out a little bit further, a collision between the physical sciences and mathematics, statistics, and computer science. And we feel like we're gaining new insights into fundamental physics facilitated by these advances in artificial intelligence. We hope that that there'll be a two-way flow of information. And that's in part why I'm so excited to be directing this new Institute for Artificial Intelligence and Fundamental Interactions, that there's many other fields of science that are extremely data rich and that would benefit from techniques like this, techniques where you think about the structure of your data set, think about the structure of your problem, encode your physics knowledge in there, and in certain cases, be able to use machine learning techniques to do something that you didn't even know, didn't even have a language for talking about before. I didn't know what it even meant to talk about the dimensionality of the space of jets until we had this idea from optimal transport. So the goal of our institute is to do machine learning that incorporates first principles, best practices, domain knowledge from fundamental physics. And there's many areas that we hope to touch on using this research. And I hope I've given you just a little bit of a flavor for this today. And so let me just summarize before I open up the floor for questions. And I encourage people to ask all sorts of questions about this work. And I have many backup slides if people are more interested about anything that I said. But just the summary, the particle physics 101, that high energy collisions can yield insights into fundamental physics, and machine learning offers powerful new tools to analyze collision debris. From a data science perspective, what is a collider event? It's just an unordered set of particles describing the energy flow of jets. And this inspires network architectures designed around this principle of permutation symmetry and this principle of infrared and collinear safety coming from this energy flow paradigm. And then when are collider events similar? Well, they're similar when their energy flows are similar. And this led to this new unsupervised learning strategy and this introduction of event geometry, and something that we're really excited to see develop over the next years. So thanks very much, and looking forward to your questions.
Thanks so much, Jesse. Whoever wants to unmute is welcome. Okay. So I see we do have a few raised hands. Marek?
Yes, hi. This was fascinating, and I have a question from our field, high energy physics, but a slightly different domain. In the last few years, there has been a large number of experimental discoveries of exotic hadrons, which are candidates for multi-quark states, tetraquarks, pentaquarks, and so on. And one of the most difficult tasks experimentally is establishing their spin and parity, which is canonical way is something called partial wave analysis, which is extremely time consuming and tedious. Question to you is, can these methods be applied to that problem?
So, so I don't know specifically for that problem, but let me just say generically, if you have a totally well-defined generative procedure, that is, if I give you full information about an exotic hadron and you know how to predict all the partial waves from that, if you have that forward knowledge, then machine learning can take many, many examples of that forward knowledge and then basically be able to invert it for you. So if you are able to generate large synthetic data sets where you trust that the inputs about the properties of hadrons map out in a trustable way to something that you would see in the data, if you had that forward process, then machine learning gives you an opportunity to do the reverse process. And normally matrix inversion is an ill-posed problem, and it's no different than in machine learning. And so to do this inversion, you have to encode your prior knowledge about what's going on. You have to put in biases, but hopefully you put in those biases in a way that's physically motivated in order to come up with unique solutions for that inversion. But as long as you have the forward process, then you can invert it. And one of the things that we've thought about is doing this in the context of detector corrections, where if you have a detector simulation, you can throw your data through, and then you can try to invert it back. And if people are interested, I can show you a backup slide talking about how you can actually do that inversion using just the tools that I showed here today. And I can do what to me seems like a miracle, just starting from this hello world of jets. I can build you up to something that I can actually correct for detector effects.
Yeah, this is conceptually similar to the picture of the library that you showed.
Exactly. And of course, in the one I showed before, it had never seen anything else before. It only seen that one picture of a library. But if we can generate lots of synthetic data, you can actually do an even better job of predicting what's going on.
Okay, thank you.
Asher?
Thank you. Very nice talk. I'm curious, the holy grail of particle physics is, of course, unifying. And finding maybe a unifying principle behind the standard model.
Mm-hmm.
So what are the perspective using those new methods to reach the Holy Grail?
So this is an excellent question. Let me, unfortunately, let me go to my backup slides. Sorry, I have too many of these, but I can't figure out, oh, there we go, I can slide now. Just give me a moment. Okay, so so the short answer to your question is that I don't know, but there is some hints of it in this idea of energy flow. So here is this energy flow observable. And this was something that was introduced in the 1990s. Oh, sorry. First introduced in the 1970s by people who were studying energy correlators. So basically saying, how much energy do I have in one part of my detector and how is it correlated to energy in another part of my detector? And this idea was revived in the 1990s by Kachoff, who basically argued that this is the way that we should study things. And then Hoffman and Maldacena, and I think it was 2008, did a study that said basically in the context of a conformal theory, if you can map out all this energy flow information, you've actually captured the information that you'd like to know about your conformal field theory. And there's a bunch of us who feel that this energy flow concept may be a way of specifying all the information that I care about in a theory, at least in principle. So you've probably heard of people doing the amplitudes program, where you try to build up amplitudes from their kind of fundamental symmetries and properties. But the problem with amplitudes is that scattering amplitudes are not infrared and collinear safe. They're formally not really well defined. And of course, there's techniques of dealing with that. But this energy flow idea is one that sidesteps that completely. And it may be that the way that we specify the flow of energy in a theory, that actually corresponds to, in some sense, the best way of characterizing what a theory corresponds to, if you can do basically arbitrary point correlators. And one of the things that makes me optimistic that this energy flow or energy correlator picture might be the right way of analyzing data or thinking about data is in some work that I'm doing currently with Patrick Kamitsky and Ian Molt, where we're again studying this kind of dimensionality or change in the behavior of jets, but now from this energy correlator picture. And what we can see is actually pretty clear phase transition between the hadronic phase and the partonic phase using this energy correlator idea. And so this is something that I didn't know that I could do with collider data. And it gives me some sense that maybe this energy flow idea is the one that kind of unifies different ways of talking about theoretical structures. So that's kind of a partial answer to your question, or at least hopefully gives you some food for thought.
Thank you.
Itai?
So this is also sort of a big, I mean, like looking from above question, but can you use this also to maybe somehow learn stuff about non-perturbative quantum homodynamics? Because, I mean, this sort of seems like you have the labels, right? Because you sort of know what happens. You don't know how to compute things. So maybe you can teach it Feynman diagrams of non-perturbative stuff, basically.
So excellent. So I think this plot here shows you already an example of that from a data science perspective of learning new things about hadronization that you didn't know but for these techniques. And in fact, the particular slope here would correspond to some properties of the hadron gas that you'd like to understand. So the thing that you said, I need to reveal myself. That I said if I had labeled examples, then there's all sorts of things that I can do. But of course, a jet doesn't come out from a collider saying, "Hi, I'm a quark. Hi, I'm a gluon." In fact, quarks and gluons don't even make any sense because quarks and gluons carry color charge, but hadrons are color neutral. So actually, there is no unambiguous mapping of what you mean by a quark and what you mean by a gluon. And so you could say, wait a second, Jesse, what did you just tell me of this whole colloquium? You told me that I could use machine learning, and now you're telling me that the training examples that you used, you couldn't even gain access to. So like, what are you even talking about? But it turns out, and I think I don't. Oh yeah, okay. So it turns out that there is a machine learning technique that's used in natural language processing called topic modeling, where you can think about it this way. Someone hands you all the papers on the archive, and removes the category labels. You remove HepTH, HepPH, you know, all those. And then you say, please sort your articles into categories, but I'm not going to tell you what the categories are. And that's a natural language processing technique called topic modeling. It's also known as blind source separation. It's something that's used for analyzing the CMB already in the cosmology context. And basically what it does is it takes these collections of words and then figures out how to separate things into its individual components. And you could even figure out, you know, this paper is, you know, HepPH with a cross list to HepTH. You would be able to learn that by doing this natural language processing technique. And this actually gives us a strategy for actually defining what quarks and gluons are. And then, as you say, you could exactly do what you proposed, which is then analyzing quarks and gluons and try to build a generative model that explains those radiation patterns. That generative model would need to have a non-perturbative component, and your hope would be that that non-perturbative component would be one that could be interpretable. But the starting point is actually getting your hands on good labeled data, and remarkably, from natural language processing, there are strategies that one can use to do precisely that.
So it is being done, or it has been, so?
It is. This part, the thing that's on the screen, this has been done. And in fact, we've done it in the context of heavy ion collisions, where we're trying to understand how quarks and gluons properties are modified as they plow through a droplet of quark-gluon plasma. But in terms of the non-perturbative thing, the challenge there is properly specifying the problem. What are you trying to do? The machine will only do what you tell it to do. So I showed you these psychedelic images where I'm able to do verification of the machine learned answer. But I could only do that because I encoded the machine in a way that it could speak my language. I encoded this energy flow idea, and then that energy flow idea was what the language that the machine spoke back to me in. In the case of non-perturbative modeling, you'd have to say, look, I want to model things in terms of my various two-body, three-body, whatever interactions, but you have to give it some information about how you want to model the process if you want to have a chance of actually getting out more than you put in.
Kobe?
Hi, my question in fact is a continuation of Itai's question. I mean, it's very impressive, these tools that you showed us about analyzing experiments, but the real question is, can we understand physics better? For instance, the physics of hadronization. Can these programs teach us of how to deduce the PTI algorithm from basic QCD, not from some from models? And it's not obvious at all that we can really get a broader, a better picture of the physics of QCD in the soft non-perturbative regime.
Yeah, so in terms of the modeling side, I'm not as confident about the modeling side because I'm not even sure what the well-posed problem is. So one way of saying it is, imagine someone gave you the blackbody spectrum. They gave you all this data about blackbody spectra. From that, how would you deduce that photons are quantized? How would you deduce quantum mechanics from that? And the answer is that you don't just look at blackbody spectra. You also need to look at hydrogen spectra. You have to look at other types of quantum phenomena in order to realize that there's an underlying process that's intrinsically quantum to it. So if you want to learn about non-perturbative dynamics, in some sense, you need to ask a question that's complicated enough so that the machine would have to figure out that somehow the non-perturbative dynamics is what it needed to learn. Because otherwise, it's going to find whatever shortcut it possibly can in order to understand what's going on. So one way of trying to gain information is to try to actually restrict the machine in some way. So for example, this is not for non-perturbative modeling, but for perturbative modeling. If you assert that the process of jet formation is a Markov process, that is, you have emissions that happen one at a time, and you only have memory of your most previous state for figuring out what radiation you're going to get next. If you assert that it's a Markovian process, and then you try to ask, can you match the data using just a pure Markovian process? The mismatch there tells you something about the non-Markovian nature, which we know actually has to be there because of quantum mechanics. And so one can try to be kind of clever about the way that one poses questions in order to be in situations where, let's say, the failure of the machine to be able to do something actually turns into some knowledge. But I would say that these techniques, we aspire to have them teach us new things, but we have to learn how to use them. And just like we had to learn, new mathematical techniques like calculus in order to take advantage of them in the physics context, we're gonna have to learn how to take advantage of these machine learning techniques and figure out how to translate our problems into a machine learning language in order to learn more.
We'll have one last question, Rotem.
Hi, thank you for the talk. I'm a big fan of your work. I wanted to ask regarding the trade-off between how much we understand what our neural networks are doing to how well they perform.
Yeah.
It seems to me that you have to impose certain limitations on the network in order to receive more information from it other than input and output. And I wanted to know what you think about that and how that type of problem should be tackled.
Okay, so first, this is an excellent point and one which we've been striving for in the examples that we've been exploring, is basically how small can I make the network and still get out excellent performance. And I can't find the slide for this right now, but we checked the quark-gluon classification power as the size of that latent dimension. And in order to get the best classification power, you needed something like a latent dimension of 32 or 64, something like that, which is still quite a lot. And some work that I'm doing with an MIT undergrad is actually teaching the machine something new. In particular, I'm teaching the machine about relativity and the fact that you should take Lorentz invariant dot products. The machine didn't know that was a good thing to do. I'm giving the machine that extra information. And when I give that machine that extra information, instead of needing 32 or 64 latent dimensions, it looks like you can get the same classification performance with just one, which is to say that physics knowledge that we all know, you just give the machine access to that bit of information, and it's able to do things in a much more compact and interpretable way. So I don't have results like that to show, but I can show this plot here. This is what happens if I restrict my output to 2 latent dimensions. This is basically saying that the machine can only look at 2 parts of the jet, the inner core of the jet and the periphery. That's what's shown here. I'm seeing the inner core of the jet and I'm looking at the periphery. And you'd say, oh, the machine's pretty smart. It's learning to learn about what particle physicists would say the collinear physics and the soft physics of QCD. But what's remarkable is that no human physicist had ever, to my knowledge, actually made this distinction so clearly. In work that I was doing in 2017, I was trying to measure things in terms of polynomial moments. And this Gaussian and this kind of logarithmic thing don't look polynomial at all. And so I spent, a year and a half of my life chasing this problem of quark-gluon discrimination without realizing that I should really cleanly separate out soft and collinear. And so here's just a plot showing efficiency versus rejection for quark versus gluon. And these gray dashed curves are all the things that I was trying. All the things that I, as a human physicist, a domain expert, was doing based on, in some sense, the incorrect way of thinking about the information of the problem. The machine taught me a better way, that's shown in green. I get better performance. And then I look at what the machine does and then say, can I do a first principles inspired kind of analysis of what's going on? Can I reverse engineer what the machine did? And the reverse engineering, shown in purple, is basically figuring out, hey, machine, how did you solve this problem? And then we can take that information and again feed it back into our network. So I think while there's this push towards more complicated networks and getting better performance, my feeling is that it's going to be much more of a balance between these things, and we're going to try to ask the question, why is this machine doing better? And when it does do better, if we can understand it, then baking that in, and then it will be able to do it, potentially even better in the future. But this at least is one example of realizing that the machine actually has done something that I didn't know how to do, and that for me is quite inspiring.
So, thank you so much, Jesse, for a wonderful talk. And I think I learned here how to clap, at least virtually. And so that's it, everyone, for today. Thanks for joining, and hopefully we'll see you all again in 2 weeks for our next Israel Joint Physics Colloquium. So let's give Jesse again a big thank you.
thanks so much, everyone. And I hope the next time I'll be there actually in person in Israel to see you all.
Okay, looking forward. Stay safe and healthy, everyone. Take care.
Thank you.
Thank you.